whole thing, although you see that's looks really messy, but keep these things in mind because this is a linear system. The force excitation is also linear. So we can decompose the linear components into individual ones. Then we tackle it with our fundamental templates from chapter 3. And we obtain the individual response to individual components. We simply, in the final, we take summations. The whole thing can be implemented in Excel spreadsheets pretty easily. Okay, so again, in chapter 3, I recommend you, and doing the exercise, you create one Express spreadsheet and then document all the equations. Then basically you simply copy and paste that block into so many, and then you simply to the final say 10 terms. Here, those kind of things is 10 terms, for example. And I can tell you for any general functions, if we express in terms of this kind of the combination of the harmonic terms, actually this is called the Fourier series expansions. For many general force, and if you would do the Fourier series expansion, then the higher order terms, the magnitude of the higher order terms become very small. Okay, so in practice, if you have a spreadsheet built up, basically you copy and paste to build up corresponding terms. And usually the first 5 or 5, 6 terms will give you pretty much good the estimations. Okay, so this is a concept here, and let me see, do we have an example here? We do have one example here. So before I move on to example, this one basically provides the theoretical introduction. Okay. Before I move on, any questions? No? Good? Okay. And in the PowerPoint slides, I only give the outlines, the big pictures without details. If you like, this could be the last chance. If you like, you can use your cell phone to take pictures to help yourself. And or otherwise, once I rest it, probably we don't have any time to go over this again. And probably you take the 2 sides, and then you can find the printer to print it out and attach to whatever the slides you have. Okay. Good. So right now, let's look at a few examples here. So let me erase this part. And Ft is this. And this is a square pulse. This has a period t, so t and 2t. Okay, so this is 0.5 t. So basically, this is a periodic function, and this is we call the 50% PWN, 50% duty cycle square signal. Okay, and not square rectangular signal. So for example, here the magnitude is up now. Okay, so this is a very typical the things, and then this can be precisely achieved by, if you have played the Arduino, so you know that one, and that can be produced from that board, okay. But however, that kind of board, if you have seen, if you want to play, actually in our department, I purchased quite a few sets, and if you like, you can come to me. You can check out the box and play around. That output from that board is small signal, and usually the range of the voltage working in that one is between 0 to 3.2 or 0 to 5 volts, okay? And the current is calculated in the unit of the milliamp, so that's a very small power. But that one basically is working with controllers. If you would really want to use that one to produce, then you have to link to certain board to amplify the signal to drive the motors. In this way, the motor can be useful for function with other conditions like the driving force. Okay, that's the concept here. But anyhow, we want to find a steady-state response to such a force, and we know this is periodic. However, this periodic, if I want to give these kind of things, and applied our concept like this, so the very first step, someone have to take the dirty job to convert the given information into such a form. So that means you have to conduct the Fourier series expansion. Okay, this is periodic functions, and all the periodic functions can do the Fourier series transform to get to obtain the we call it discrete Fourier series. Okay, so that form I have done for you for the first time, and that means next time will be your turn. Okay, so but I will give you a review about the Fourier series expansions. So for this one, if we apply it, then that basically can be equal to ft of this one will be equal to f0 divided by 2 and plus 2 f0 divided by period, and then pi. Sorry, this is yeah, okay, and sine omega t plus 2f now 3 pi and sine 3 omega t, and then plus the higher order terms. And higher order term, you can pretty much guess the template. So that would be, say, divided by 5 pi and sine 5 omega t, divided by 7 pi sine 7 omega t, etc., etc. Okay. But again, you can see the magnitude. This is 2 divided by pi, 2 divided by 3 pi, and the next term will be 2 divided by 5 pi, 2 divided by 7 pi, etc. So basically, the magnitude is getting smaller and smaller. So we can, if you like, we can drop it. Okay, so for our exercise, I simply take the first 3 terms. Okay. So right now from here, we can simply take that form here. So therefore, the steady-state response will be, so let me take up the template. So right now, we only have 3 terms. So basically, the first term corresponding to this one. So again, if you have the lecture notes, take up that with you. Corresponding to the first term, that is the magnitude of the force, okay? And then we plug in, keep this carefully, okay? 1 minus r squared plus 2 zeta r squared. For the first term, again, for this case, let me write it up. R, what is R? R is the ratio between the working frequency to natural frequencies. For this constant term, the working frequency equal to 0, right? So this is R equal to 0. So the first term equal to R equal to 0, Okay, and then corresponding to the second terms, I'm using a different color, and plus the second term. For the second term, the magnitude of the excitation is 2F0 divided by pi. Oh, sorry, if I will take this one, then I forgot one term. Okay? This one I need to divide by k, because I take, if you remember that formula, if I would take the r, then numerator should be delta st, right? Okay. So this one again, the same template, 1 minus r squared plus 2 zeta r squared, and for this case, what is r? For the second term, r equal to, again, that is a ratio between the working frequency, which is omega, divided by omega n. So here, omega divided by omega n. Okay, and the third term plus the third term is corresponding to this one. So for the third term, again, the magnitude, that is delta st, and that is 2f now divided by 3 pi and divided by k. Okay, and this one again, 1 minus r squared plus 2 zeta r squared. And here, for this case, what is r? So for the third term, r is the working frequencies, the ratio, and that is 3 omega. This is our working frequency. Okay, divided by omega n. You good? So this is the answer. So basically here I want to emphasize again, everything is in certain template. Then basically if you have program, then basically you can simply using the for loop or do loop, repeatedly adding the more terms. Okay, so here for demonstration I only have 3 terms, but using program you can easily extend it into many terms. Good? Okay, and that's yes?
And you don't need to multiply by sine.
Oh, yes. Yes, super. I will give 1 point. And yeah, so remind me. So I forgot. This is only magnitude, and this and this is that's it, and this magnitude. This is taking sine, so that is sine and omega t minus v, and where the v will be equal to arctangent, and c omega k minus c m omega squared. Okay, so this one multiply with sine 3 omega t minus v. So why not let me using the different notations. So here is 3, okay? So arctangent c times 3 omega and k minus n 3 omega squared. Okay, so to distinguish the different numbers, so let me say this is v1.
Do you want those in the same terms? Or do you want to use r instead of for your inside your feed? You're using c and omega, like c omega.
Yeah.
You want
So
by k?
yeah, if you like, we can use the omega. So using r. So for example, this one will be equal to arctangent. What's that? 2 zeta r, right?
Mm-hmm.
And 1 minus r squared. So for this case, the r equal to whatever this number here. Yeah. Either way. Yeah. Okay, the same thing. If you like, this one can be arctangent 2 zeta r, and then 1 minus r squared. So for this case, r equal to omega divided by omega n. So this one, r equal to 3 omega n. Okay.
Question.
Yes.
So, if, for example, the Fourier series was with cosine instead of sine,
Yeah,
then those
that's
would
a
all be
cosine.
cosine.
You simply take cosine.
We're just copying. Okay.
Yeah, and again, whatever the input, the output is always to follow the input pattern. when it follow it, because the system is just like, because system have some certain inertia and damping, so that will cause some delay. The delay is explained by the phase angle. Okay, so whatever sine or cosine, you follow that pattern, and then with some phase angle.
Is there a phase angle slightly different?
The phase angle, right now I'm teaching you is this. If we follow the same form of the excitation, then phase angle basically is in terms of this one. And if you like to have the, say, for example, answer to your question in specific, if we have an input is sine, however, if you like to take the output response as a cosine, then the phase angle would have the 2 pi, the 90 degrees in difference. But we simply pick one. We simply pick one standard form and for communication. Don't confuse anyone. Okay, I know you're good, but don't confuse anyone. Okay, even confuse myself. That would give myself a little bit hard time in teaching because easiest way is we simply pick up one standard form, just like this, and then that'll be good enough. And then if you would be more time, then you can dig out more other extended equivalent standard form, and that's on your preference. But that will be sufficient. I just want to make sure everyone know how to do it, and we communicate with some some platform, and that's it. That's it. Okay, so that is an example, and so today we will stop here. And we will have a few more examples, but again, that example, as long as we know the force being decomposed into some term, basically the work is really repeated, nothing special. Okay, so now I can tell you the key work on those one. The first one on your understanding of decomposing the input into the form, then calculate corresponding output form to individual components, take some actions. This is easy. The remaining would be, given any type of the force, how do you decompose into this way? Usually this term is not given. Those kind of expansion is not given. So I would say coming back after our test Monday, I will review the Fourier series transform, and then in this way everyone would at least know how to do it. And correctly or not, then that is not my business. Okay, thank you.